Afternoon. Can you hear me okay? My name is Hui Lei. I will be discussing some challenges and opportunities for productionizing AI. There has been very high expectation on what AI can bring to the business world. Unfortunately, the reality has fallen short. Less than 10% of AI pilot projects have reached full-scale production, and only 25% of companies have revenue-generating production AI systems. You may say, wait, don't we have many tools for building AI applications already? Why is this still so hard? Indeed, there has been a proliferation of tools in the broad area of AI, spanning infrastructure management, data integration, data processing, machine learning, and various domain-specific services. In fact, the proliferation of tools is part of the problem because new tools keep surfacing, existing tools keep evolving, and no tool suits all use cases. And also, existing tools require deep expertise and skills which are not readily available in many companies today. And integrating those tools involves glue code, which often incurs large overhead and deep technical debt. There's some relief from machine learning platforms. This includes platforms from Microsoft, Google, Amazon, and IBM, as well as open source software such as Qflow and MLflow. Those platforms provide a variety of capabilities such as data ingestion, analysis, and preparation, as well as model building, and tuning, and deployment. Apparently, those platforms are not adequate because many companies like Facebook, Airbnb, Uber, and LinkedIn are still building their own proprietary platforms. So what are the problems? Let me quickly sample some of the challenges in building production AI systems. Production AI systems are very different from lab prototypes. They involve a lot more than machine learning. In fact, we argue that there are three distinct building blocks for production AI systems: data pipelines, model pipelines, and insight pipelines. Data pipelines are processes that generate data sets to be used for machine learning. And model pipelines are processes that build and tune models based on the data sets. And insight pipelines are processes that derive insights using data analytics and model inference. Existing machine learning platforms are mostly concerned with the model pipeline. They start with an integrated data set, and they end with deploying a trained model. However, in reality, it takes a lot of work to generate that integrated data set from heterogeneous and siloed data sources. And also, generating insight goes far beyond making inference from a single deployed model. That's why we also need data pipelines and insight pipelines. In addition, in a production AI system, we also need to cope with infrastructure provisioning and optimization. We need to ensure that the insights generated are trustworthy, unbiased, and explainable. We need to streamline the development, integration, and delivery process end-to-end, and we also need to support AI applications in a hybrid multi-cloud setting. And most of these capabilities are not in the scope of today's machine learning platforms. Data is the fuel for AI, and data comes in many different forms, right? Tabular data, documents, key value pairs, graphs, audio, and video. And different kinds of data are stored in heterogeneous repositories. And in order to apply machine learning, we need to be able to integrate data from siloed repositories and generate a coherent data set. So far, many different approaches have been developed, but they all have their own pros and cons. For example, data lakes, right, bring data physically together, but data in the lake remains disintegrated logically, and data is often stale and incomplete. And virtual distributed file systems, such as Alluxio, impose a simple abstraction based on files, but that's too primitive for many purposes. On the other hand, distributed query engines, such as Presto and Impala, right, they provide a high-level abstraction, but they require the content be structured and have a well-defined schema. And data flow engines, such as Spark and Flink, offer the most flexibility, but they leave a lot of low-level decisions, such as caching and push-down processing, to developers, and that's not desirable at all. Many people made the assumption that after I train the model and deploy the model, I got everything I need to make predictions or generate insight. That's a myth, because insight generation often involves a whole pipeline of components. An insight pipeline very often, right, uses multiple models along with components for data pre-processing, data post-processing, integration with enterprise backend, monitoring and reporting and dashboarding. And operationalizing such a pipeline actually is very complicated. It presents a lot of challenges. For example, how do we make sure that the entire pipeline meets the service level objectives end to end? Where should we deploy each pipeline component? Should it be deployed in a container or through a serverless function? Should it run on GPU or CPU? And how many replicas of a pipeline component will be appropriate? And what's the right size to batch? What's the right size to batch incoming requests and so forth? And also, how do you ensure the quality of the insight generated? How to detect and mitigate data outliers, data drifts, concept drifts, adversarial attacks, and prediction biases, right? So, and most of these functions basically have no platform support at the pipeline level. So, challenges also bring about opportunities for research innovations. First, how do we design a solution platform for integral AI development, right? Such a solution platform should support the development and operations of data pipelines, model pipelines, and insight pipelines in a consistent manner. And that translates to a common set of programming abstractions, right, for all kinds of pipelines. Also, we need an integrated DevOps process that streamlines the entire solution across data integration, model building, and insight generation. Such a solution platform should also provide a unified framework for managing all kinds of AI assets, data sets, models, and code, right? AI asset management needs to be based on a common asset catalog and an overarching metadata schema. The solution platform should also automate the provisioning and optimization of the underlying infrastructure, which is often heterogeneous and across hybrid multi-clouds. Overall, we want a solution platform that provides a one-stop shop and an integrated experience for all personas on the solution team, so that data engineers, data scientists, machine learning engineers, software engineers, and IT engineers can all collaborate efficiently. And in that way, we can significantly improve time to value for business AI. Another area of innovation has to do with data virtualization. The idea here is to tackle the silos in data sources and data processing engines. Work is needed on 3 layers: data access abstraction, engine orchestration, and data orchestration. The data access abstraction layer will expose both declarative and procedural interfaces for accessing and processing data. The interfaces should be general enough and accommodate all kinds of data sources and data processing needs. And the engine orchestration layer will implement the interface by pushing down processing to off-the-shelf analytics engines, including batch processing engines, stream processing engines, and query processing engines. And the data orchestration layer will move data and compute together for better performance. A key research question here is, how can we design optimization techniques for both engine orchestration and data orchestration? Basically, the data virtualization technology, right, should simplify development and accelerate development by masking the heterogeneity in data sources and data processing engines. At the same time, you will scale data access and analysis by separating compute and storage, and also by incorporating techniques such as intelligent caching and near data processing. We mentioned that insight generation takes more than model inference. Here we show some examples of multiple components used together to generate insights. In the first example, this is for classification, right? We start with basic data transformation. Then we use a model ensemble where multiple weaker models are used to classify an item. And the individual classification results are then combined to generate the final outcome. And in the second example, we have an image processing application. It starts with image cropping and resizing, followed by a sequence of neural network models of increasing complexity. A more complex model is used only when the previous models are not able to classify an image with high enough confidence. And in the third example is for video analysis, right? We first segment a video, and then we invoke separate models for face recognition, object detection, language translation, and audio analysis. We also have some other examples for defense against adversarial attacks and prediction debiasing. The message here is that using an assembly of reusable components can bring many benefits, right? It can significantly improve the accuracy, throughput, robustness, and fairness of insight generation. You can also simplify model building and training and reduce development cost. Obviously, there are research questions that need to be answered. For example, how to operationalize insight pipelines in terms of deployment, orchestration, monitoring, and governance. And also, how do we, for example, how do we allow such a pipeline to be defined very easily, even by people who are non-tech savvy? And also, how do we generate insights within a matter of milliseconds when a complicated pipeline is run against high-speed data streams? So let me leave you with a summary of what we just discussed in terms of challenges and innovation opportunities. We feel that an AI industrialization is an important area, and we certainly welcome opportunities to collaborate with the open source community to advance both the state of the art and the state of practice. That's all.